Chapter 11 is all about molecular geometry and a little bit further look into bonding. In Chapter 4, we took a look at different types of bonding, whether we were looking at metals and nonmetals or two nonmetals together, and we classified those in two different ways. So our first aim is to learn about ionic and covalent bonds and then to explain how they're formed. And the second is to specifically focus on polar covalent bonds. So remember, a bond is just a force that holds two atoms together. So we're really looking at the type of connection between the atoms that we have. And we talked about two different types of bonds, either covalent or ionic. So when we're looking at covalent compounds, we're talking about those that exist between two nonmetals. So anything that is on the right side of the table, remember that's where our nonmetals are. So any two or more elements that come from the right side of the table will form a covalent bond. They're not transferring their electrons, they're sharing electrons through their valence shells. So no charges involved here. When we're looking at an ionic bond, we're looking at elements that can give up electrons, and in giving up a negative charge, they become more positive. And remember, these are those that are on the left side of the table, the metals, combining with something that forms a negative charge, something that will accept an electron to fill its octet. And as it accepts electron, it becomes negative. So this was something like, this was a metal and a nonmetal. This could be something like NaCl, whereas the covalent compound would be something like CO2. So we're looking at the difference between ionic and covalent, but specifically here focusing on the difference between nonpolar and polar covalent. Ionic bonding, remember, is a transfer of electrons. We have a cation and an anion. Remember, the cations are positive. And we're talking about the difference between a metal and a nonmetal, or the attraction between a metal and a nonmetal. So you can see in the top picture, we have sodium. Sodium is going to lose one of its electrons, and it wants to do that to reach a more stable configuration. It's in the first column. It has one electron in its valence shell. It's going to give up that one electron. And what's going to happen when it gives that up is it's going to be transferred to something else that needs it. So chlorine needs one electron to fill its valence shell. When that happens, sodium was neutral and it lost one electron to become positive 1. Chlorine was neutral and it gained one electron to become negative 1. So at this point, we have a positive 1 charge and a negative 1 charge, and we're looking at the electrostatic attraction that binds them together, because we know that opposite charges attract. And then now we transition into covalent bonding. So remember, covalent bonding is just a little bit different because charges aren't involved here. We're only looking at a sharing of electrons because we're not dealing with transferring of electrons as we do when elements become ions in the case of a metal and a nonmetal. Here we're looking at two nonmetals bound together, and these are bound in a slightly different way. We don't have the electrostatic attraction that we have between a positive and a negative ion. Instead, we have overlapping of the valence shells. So we have the electrons from hydrogen, you can see here are in red, and those overlap with the carbon atom valence shell. So remember, carbon is in column 4, 4 electrons in the valence shell, which means it can accommodate 4 more in terms of overlap if it wants to complete its octet. Now, the difference between nonpolar and polar covalent bonding, when we think of the term polar, we think of the poles, positive and negative, or opposites. So what we see here is an unequal sharing of those electrons that are overlapping. So we have one atom that's slightly negative and one that's slightly positive. And remember, this doesn't really happen, it happens to a great extent in ionic bonding. That's why we don't have to classify ionic bonding as polar, because by its nature, it is polar. There is one positive and one negative. So in this specific type of covalent bonding, we have one that's slightly negative and one that's slightly positive. So you can see here that one of these atoms, the chlorine atom, is quite a bit more aggressively pulling on those shared electrons than hydrogen is. So we use these notations to denote something that's partially positive or partially negative. That's that delta symbol. So we can write it out something like that, partially positive or partially negative. Almost everything, unless you're bonding something to itself, is going to be positive or negative relative to the other atom that is bound to it. So in this case, we see that fluorine is a bit more partially negative than hydrogen is. So fluorine is going to pull more of the electrons to itself. So when we're talking about polarity, we want to look at how to classify each of these types of compounds. So a covalent bond is going to be what we would consider the least polar. We can have very equal sharing in a covalent bond. In a polar covalent bond, we start to see a little bit of that charge separation. We start to see something becoming partially positive and something becoming partially negative. And then, of course, ionic bonds, just by the nature of the bond themselves, are the most polar. And then that's 11.1, just looking at the difference between ionic, covalent, and polar covalent compounds. In 11.2, we need to understand the nature of bonds and their relationships to electronegativity. So electronegativity is how we tell that something is going to be more or less positive or negative. Electronegativity is the ability of an atom to attract shared electrons. So that partial positive or partial negative aspect of the bond is determined by the electronegativity of that atom. So it's a measure of how bad an atom wants an electron. So the higher electronegativity value something has, the more it's going to pull those electrons towards itself. So you can see here that fluorine is the most electronegative element. And don't get too hung up on these numbers. These numbers are just kind of arbitrarily chosen in relation to fluorine. So what we need to remember about this is the general trend that we would see. And we did this back when we were doing our trends project in chapter 4, where we were looking at the electronegativity trend. So remember, fluorine is the most electronegative element. We see it decreasing from top to bottom, and then we see an increase from left to right. So the highest electronegativity is going to be at the top right. The lowest electronegativity is going to be at the bottom left. This gives us kind of a general outlook on comparing electronegativities. We don't need to know these numbers. We don't need to memorize them. We just need to be able to know if they're going to be different at all. And unless something is bound to itself, it's going to be different. So again, this is just another way of looking at the trend. So we see in these pink arrows up here, we have increasing electronegativity from bottom to top, and then again from left to right. And that's why we see the general trend goes in this direction, with fluorine being the most electronegative. Now, in general, we can assign electronegativity differences to different bond types. So, zero electronegativity difference refers to a purely covalent bond. Oxygen's electronegativity, if we take a look back at that slide, is 3.5. And if I have another oxygen, so I have O and O, 3.5 minus 3.5 gives me zero electronegativity difference. Zero electronegativity difference is a purely covalent bond. There is no one atom that wants to share those electrons any more than the other one does. Now, anything between 0 and 1.7 is going to be what's called a polar covalent bond. So, for example, if I have an oxygen and a fluorine, I'm looking at a difference of 3.5 and 4.1. And don't get hung up on the negatives here either. We're just looking for the absolute value of the difference. So 4.1, the difference between 4.1 and 3.5 is going to be 0.6. Now, this puts it in the polar covalent range, which makes sense. We're talking about a covalent bond. We're talking about two nonmetals together. And we're also talking about an electronegativity difference, which means one of them is going to want electrons more than the other one does. Anything above 1.7 is going to be a purely ionic bond. And this number can vary a little bit. And like I said, don't get too hung up on these specific cutoffs. It's going to change depending on what book we look at anyway. But in general, anything with a large electronegativity difference is going to be an ionic compound. If I'm looking at H2, the way I would go about calculating this is to say that hydrogen is an HH bond. Hydrogen is 2.1, and I'm subtracting from that a 2.1, which gives me a difference of 0. So remember, difference of 0 means that no one element is pulling on the electrons any more than the other one. HCl means I have a hydrogen, which is 2.1, and a chlorine, which is 2.9. So the value of the difference between these two is 0.8. 0.8 we can then classify as polar covalent. And this one, remember, was covalent.